All right, everyone, welcome to today's Explainer. We are taking a rigorous college lecture approach today to completely break down the Pocketflow framework. We're going to explore how incredibly complex agentic behaviors can actually emerge from a place of extreme minimalism. Look, if you're an AI or full-stack engineer, you know firsthand that building reliable, multi-agent systems is arguably one of the hardest challenges in software right now. We are constantly battling complexity. So today, we're dissecting a framework created by Zachary Huang that completely flips the standard heavy development paradigm right on its head. Grab your notebooks because we are diving deep into the architecture.
Here's our syllabus for today's lecture. First, the AI orchestration dilemma. Then, core architecture and abstractions, followed by the 100-line core. Next, we'll cover lifecycle and performance modeling, ecosystem and language ports, and finally, production patterns and trade-offs.
Section 1. The AI orchestration dilemma. Heavy frameworks versus lightweight control.
To really understand this, we have to talk about the pain of the current landscape. You just want to chain a few LLM calls together, and suddenly you are forced to integrate these massive, bloated frameworks that bundle vector databases, memory tracking, and proprietary clients. It's a maintenance nightmare that leads to total vendor lock-in. Now, with that in mind, look at this single number, 100. Pocketflow reduces core agentic orchestration down to a minimalist 100-line Python implementation. Literally, just 100 lines. It completely strips away all those bundled LLM wrappers and database connectors. You're left with a pure, zero-dependency control flow graph. This perfectly insulates your core logic. If an AI provider changes an endpoint tomorrow, your orchestration remains completely untouched. Switching models becomes incredibly simple and entirely risk-free.
Section 2. Core architecture and abstractions. Building the theoretical foundation. To make just 100 lines of code do all that heavy lifting, you need some incredibly strong computer science patterns. The first one is the blackboard or shared store pattern. Instead of passing localized payload dictionaries directly from node to node, which we all know inevitably leads to fragmented states and nasty race conditions, Pocketflow centralizes the state. Think of it kinda like a communal whiteboard in a classroom. Every single processing node interacts only with this central board. They read what they need, do their specific job, and write the results back. This entirely decouples your processing nodes from downstream routing. You can add new agents or remove old ones without ever rewriting your existing node interfaces.
The second pattern is a finite state machine, or FSM, analog. Basically, your execution graph treats each node as a distinct, isolated state. The routing logic is not hard-coded into the nodes themselves. Instead, when a node finishes its work, it just returns a simple action string, like success, fail, or needs_review. The parent orchestrator then checks that string against a predefined routing table to figure out exactly which node fires next. This is a brilliant way to build self-healing code generation loops or supervised human-in-the-loop pipelines, because the routing perfectly maps to how we naturally think about workflow states.
Section 3. The 100-line core. Dynamic graph syntax and execution state.
So how does this actually look in practice when you sit down to code? Well, instead of wrestling with massive, unreadable JSON or YAML configs to define your routing, Pocketflow uses Python operator overloading for super clean graph construction. You literally write node A, right-shift operator, node B to sequence them. Need conditional branching based on those action strings we just talked about? You just use the subtraction operator. It reads exactly like a mathematical formula. And since we all know network calls fail, automatic error recovery is built right into the base nodes. It handles transient LLM API timeouts natively, attempting a defined number of retries before it triggers a dedicated fallback path. And here is a total game changer for parallel execution. We've all spent hours pulling our hair out over state mutations, right? Well, when you branch out into parallel nodes, the orchestrator dynamically clones the base node using Python's copy.copy mechanism. This isolates the runtime processes and guarantees that when you're traversing complex loops or running concurrent nodes, your context remains entirely secure. It literally stops state pollution bugs before they even happen.
Section 4. Lifecycle and performance modeling. The math behind the mechanics.
This is where structural discipline really pays off for engineers. To keep things strictly predictable, every single node follows an immutable three-phase lifecycle. First up is the prep phase. You read from the shared store and format your inputs locally. No network calls, absolutely no DB writes. Next is the exec phase. This is where you run your API calls or LLM prompts statelessly using those prepped inputs. Finally, the post phase takes the result, updates the communal blackboard, and returns that FSM transition string. This rigid separation between state management and execution logic makes testing incredibly straightforward.
Understanding those life cycles lets us model latency mathematically. If you're chaining blocks sequentially with a standard batch node, your complexity scales linearly. Your execution time is roughly your task count multiplied by remote API latency. But if you drop in the async parallel batch node, you unlock native async models. By using asyncio.gather, those sequential blocks turn into parallel lightning strikes. For I/O down LLM tasks, your total execution time stays nearly constant even as task volume goes up, dropping your wait time to the latency of your single slowest API call.
Section 5. Ecosystem and language ports, beyond Python.
Because Pocketflow is built on universal logical abstractions rather than heavy language-specific utility wrappers, it maps beautifully to other paradigms. We've talked about Python, but check out the TypeScript port. It brings vital type safety and is seeing huge adoption for web-based AI assistance. Over in Go, engineers are using functional interfaces for safe context propagation. And for high-performance systems requiring absolute guarantees, there's a highly robust Rust implementation.
Now, have you ever tried to feed a massive orchestration framework into an AI editor like Cursor? It just immediately starts hallucinating non-existent functions, right? But because Pocketflow's context footprint is so tiny, modern AI assistants can ingest the entire core orchestration code in one go. They don't hit token limits. They actually understand the framework they're writing code for, which makes autonomous agentic coding a viable reality.
Let's actually zoom in on that Rust port for a second, because it represents the ultimate lockdown reliability. For those needing absolute memory and thread safety, the Rust implementation uses custom macros and requires an explicit process state trait for transition logic. That means the compiler literally verifies your workflow routing before the code ever runs. It catches state errors and invalid transitions at compile time instead of during a critical runtime execution.
Okay, let's step through the actual design-to-code playbook for building out your applications. Step 1. Define your raw requirements. Step 2. Explicitly map out the execution flow visually using mermaid diagrams. Step 3. Design the schema for your shared store contract. Step 4. Outline your individual node definitions. Only then do you hit Step 5 and hand it off to the AI for implementation. Finally, Step 6 is configuring your reliability engineering, like retries and fallbacks. You do the high-level system design, and you let the AI handle the boilerplate.
Section 6. Production patterns and trade-offs. Deploying the framework.
Engineering is ultimately about making informed trade-offs, and extreme minimalism definitely has a cost. Look, while the zero-dependency design means no vendor lock-in, it also means you're going to be writing your own API utility wrappers for OpenAI or Anthropic. You have to manage your own database connections. Plus, because routing is evaluated dynamically at runtime, you can't just plug in a static analyzer. You have to write dynamic traversal scripts, often racing parallel container instances to acquire a lock, just to generate accurate mermaid diagrams of your actual production state.
So, putting on my professor hat for a second, here is a serious warning. If you are scaling for the enterprise, you absolutely must abandon the default in-memory dictionary. For long-running, complex workflows, if that shared store gets massive, that dynamic copy-copy cloning we talked about will cause major memory overhead. The solution? Migrate to a database-backed shared store like Redis or Postgres, and use strict pydantic models to enforce your schema contracts. That scales the system while perfectly preserving the clean architecture.
After breaking down this minimalist, mathematically sound approach today, I want to leave you with this final, critical engineering question to evaluate your own tech stack. Are you importing massive dependencies just to sequence a few API calls, or are you designing clean, explicit state machines? Pocketflow proves that sometimes 100 lines of rigorous computer science is vastly more powerful than 1,000,000 lines of bundled utilities. Thanks for coming to today's lecture, and I'll catch you in the next one.